Hi, my name is Amy Sullivan, and I'm the current immediate past president of AAAR. And it's my pleasure to welcome you to our 42nd in our monthly AS&T lecture series. This is a new initiative for AAAR being supported by the Freelander Memorial Fund. With these lectures, we hope to be able to highlight the amazing research happening in our community, tie our journal, AS&T, to other activities, and also give us the opportunity to come together outside the annual conference. And so each month, the editors of AS&T select a high-impact paper to be presented by its authors. In addition, each of these lectures is being hosted by one of AAAR's student chapters. We're also recording these lectures, and they'll be posted later to AAAR's YouTube channel, which you can access from the AAAR website under the Events tab. And so with that, I want to thank all of you for joining us and everyone who's helped to make these lectures possible. And so now I'll turn it over to our student chapter from the University of Maryland, College Park, to get us started. Thanks.
Thanks, Amy. Good morning, everyone. Today, I'm honored to introduce our speaker, Dr. Solomon Billyline. Dr. Billyline is a professor of physics at North Carolina A&T State University. He got his PhD at the University of Iowa and held a 2-year postdoctoral research fellowship at the University of Utah Department of Chemistry. His area of specialization includes experimental and theoretical atomic, molecular, and optical physics and chemical physics. Just to name a few of his many awards, he has been named Outstanding Senior Researcher twice at NCA&T and is the recipient of the Presidential Award for Excellence in Science, Mathematics, and Engineering Mentoring in 2011. His research focuses on both indoor and outdoor air quality and the health impacts in Africa. And today he will be talking to us about laboratory studies on the optical properties of aerosols derived from Sub-Saharan African biomass fuels. And so I'll turn it over to Dr. Billyline. If anyone has any questions throughout, please feel free to put them in the chat, and we'll get to them at the end.
Okay, thank you, Amy and Steph, for the introduction. And this is work that was done by my former PhD student, Megan McCree. And this is a presentation based on the paper that was published on Aerosol Science and Technology in 2025. And this also a paper that was dedicated for my 72nd birthday. So let me get the acknowledgement out of the way. This is my research group, past and present, and of course, Megan is in the group, and the postdocs and graduate students that have been working with me for the last 10 years when we started working on aerosol research. And I strongly collaborate with a group at UNC Chapel Hill, and most of the work that we do, especially the chemical analysis part, is done by the UNC group, Jason Surratt and Barbara Turpin and her students. And we also collaborate with international partners to collect the biomass fuels and filter samples. So in particular, we have Kenyatta University in Nairobi, Botswana International University of Science and Technology in Palapai, Botswana, and Addis Ababa University in Ethiopia. Furthermore, we also have collaborations with the Los Alamos National Lab, and this was a short-term project that was funded by DOE, and we took the opportunity to calibrate our ethylometer with the photoacoustic system that they had in that lab, and the funding for these projects came from NSF and DOD. Next, I'm going to talk about why African emissions, the challenges and opportunities, because especially instead of just, all of you can read the paper and understand what we did, but the motivation behind this work and what else can be done in this region is important for people who are pursuing research in their field. So I would like to spend a few minutes telling you why this is important and what the challenges are and the science questions that should be addressed and could be addressed by anyone interested in working in Africa. So African biomass emissions are 50% worldwide biomass burning derived organic emissions, and 72% of the burned area is in Africa. These are hotspots for light-absorbing organic brown carbon, and characterization of brown carbon for improved regional scale climate models is very critical. The emissions in Africa, as you can see in this cartoon, are the least studied. There are very few experimental studies and very few field work that's done in the region, despite the large emissions coming from that region. Emission sources are quite unique. These are not similar to what we experience in North America or Europe. And so these unique emission sources need to be understood. The region is also the largest global source of biogenic emissions because most of it lies in the tropics. Furthermore, these emissions are collocated with intense radiation. There is ample water vapor in the region and deep convection, resulting in markedly faster rates of atmospheric oxidation. So in general, this region will continue to exert even greater influence in future global atmospheric composition. But despite all that, very few field studies have been done in this region. And as you can see, these are some of the field studies that were reported. And East Africa, the region I'm focusing on, there has never been any field study looking at the emissions in that region. And this is a typical picture that you see when you walk in African cities. The smog is quite intense. For example, the top right figure is in Addis Ababa during a season in November, where trash is heavily burned throughout the city. And these are different regions of Africa. And as you can see, most polluted countries of PM 2.5 are listed here. So it's a region that requires lots of attention. So what we did to address this since 2019, I've been interested in regions' air quality issues. So with help with a group of individuals, we applied for a grant to NSF to conduct a workshop focused on air quality in Africa. And this workshop was initially intended to be in person, had to be changed into virtual because that was the time COVID hit us. And then following that initial online workshop that was attended by over 80 people from Europe, Africa, and North America, a follow-up meeting was conducted in Kigali, Rwanda, at the Carnegie Mellon University campus. This conference led to understanding some of the challenges, the gaps in our understanding of air pollution in the region, and it initiated air quality working groups in several cities in East Africa. And that also prompted the desire to submit proposals and to do research in that region. And that was followed by a workshop that was conducted in Chapel Hill. This was organized by myself and Professor Vizuete of UNC Chapel Hill. This was intended to develop a STC proposal and other proposals involving African partners. As you know, once we started writing the grants, political environment changed and the funding issue became very difficult, but we have had some successes in the process. And finally, there was an international conference on air pollution. This was organized by London University, Christina Isaacson, and I helped out in this coordination of this workshop. And so all these workshop results are captured in our BAMS paper that was published in 2024. So that will give you an idea of what the gaps are, what kinds of research one can do in the region. And so that would be a good introduction to why I'm interested in doing what I'm doing. And the major gaps that we identified are, there is, of course, scarce under constrained emission inventories. There is poorly understood chemical process, sparse meteorological and atmospheric, lack of continuous pollutant monitoring and lack of capacity, of course, human resource capacity. So this summarizes some of the things that could be done in Africa. There is scientific objectives, regional emissions, potential unique chemical transformations, regional meteorology. This requires expanding educational opportunities and so on. There are observational approaches establishing long-term monitoring of key primary, secondary pollutants because there are no long-term monitoring stations in the region, period. There is one that's being provided in Nairobi through Columbia University. Dan Westervelt is the person running those. There are some in Kigali, but none in Ethiopia, and I don't know if there is anything in Tanzania. Conducting field intensives with more detailed chemical and meteorological observations is needed. So field campaigns in that region, despite the fear that most have because of the logistical problems, it's doable and people have done it and it can be done. And I encourage people interested in pursuing studies over that region to plan this kind of effort. Of course, there is a MAA project which is run by JPL, which is also installing a number of high-end instruments to run some experiments in that region. So the key science questions we try to address in my group for the last 10 years is how does the molecular level composition of African fuel-derived biomass burning aerosol and optical properties change as a function of aging conditions, burning state, relative humidity, and fuel type. So the optical properties is what I'm going to talk about today, among the many activities that we had and work that was published in the last few years. We also look at does the aerosol optical properties change because of any potential molecular level chemical change. So the chemical composition studies and chemical analysis is being done and has been done extensively in our group. And also we look at does aging of primary aerosols derived aerosol gas emissions alter the aerosol physiochemical properties, including volatility, density, morphology, water solubility, and we also looked at water-soluble gas emissions that undergo cloud water processing. This was mostly work, experiment done in my lab and the analysis done at UNC Chaplin. So we're trying to address the experimental knowledge gap on African fuel-derived brown carbon. So this is a long introduction to the paper, but I think it's worth talking the context of why we do what we're doing so that people can be motivated to pursue this line of inquiry further. So for our studies, we were able to collect fuel samples from the region, from Africa. So these are the fuels that we collected, and the distribution of those fuels across the region is shown. So these are mostly very common fuels that are burned either in wildfires or in domestic use at homes because most people in Africa also use biomass fuel for cooking. So the pollution is not just outdoor due to wildfires, but there is also lots of indoor pollution because biomass is used as a means for heating and cooking. And so these are the fuels that we studied with their scientific name and their origin, mostly collected from Botswana, Ethiopia in this work. But we have recent acquisition of fuels from Kenya and from the tropics from Cameroon. And we also have actually animal cow dung, which is a very common fuel in most African households. Interestingly, that cow dung, I acquired it through Lund University in Sweden because that group also works in indoor air quality in some parts of the country, and they had collected enough cow dung to transport it to Lund University in Sweden, and I was there for a visit, and I was able to acquire some of it. So the experimental setup to do all this describes the setup to some extent. So we have a tube furnace that we initiate the fire. So this is the picture of a fire when ignition is initiated in the tube furnace, and that is introduced into a Teflon smoke chamber, which is a 9 cubic meters smoke chamber with UV lights. And then we have the gas analyzers on blue We have the SMPS, cavity ring down system, the nephelometer, the isotometer, and then we have SSM in our lab. So I'll go through each of this and separately. And the chemical analysis, of course, is done at UNC Chapel at the biomarker facility. So the burning biomass samples actually are placed in quartz combustion boats, which in turn is placed at the center of the working tube inside the tube furnace. And the temperature is set between 500 and 800 degrees Celsius for each fuel. So unlike the heating coils used to initiate burning, with which the temperature is uneven and localized, the tube furnace provides a uniform temperature throughout the sample, as the tube provides uniformly heated region of about 300 millimeters, which is about the size of the boats that we use. We also measure the moisture content of the fuels. In most cases, it's less than 10%. We calculate the burning state by using what's called the modified combustion efficiency described by this equation, and MCE of 0.99 is attributed to purely flaming. MCE 0.8 or less is purely smoldering, and anything in between. And we can also look at visually what the samples look like from the filter samples that we collect for each different burn. The brown carbon for smoldering fires and the black carbon for flaming fires and somewhat in between. Now, the tube furnace, use of the tube furnace for studying biomass burning aerosols is flexible and reproducible, as I can show in this figure here. This is a violin plot showing comparison of MCE to previous laboratory and field studies of BB biomass burning and cookstove emissions. In this case, the boxes represent the interquartile range with whiskers as the 95th and 5th percentiles of the data, and the line inside the box is the median. Violin areas enclosed by red line represent the kernel density that to show the distribution of MCs. So we're able to conduct burns of biomass fuels from nearly purely smoldering to purely flaming in a more controlled and in more controlled way, despite using 7 different kinds of fuels. We were able to burn all of the fuels within a similar range of MCE values. So the experiments are reproducible, and we felt this was a very good method. And since then, the Los Alamos group has also been using the tube furnace for similar purpose. And we also, this was actually the previous plot, and this one I'm showing is the work also published in Aerosol Science and Technology by my former postdoc, Rudra Pakral. And so one of the things we did was to measure mass mobility exponent as a function of MCE. And the mass mobility exponent relation can be expressed as a power law relationship between the mass and the C is just a constant. So the advantage of this work shows that the shape dependence on MCE. As you can see, smoldering dominated, which is less than 0.92, is represented by purely spherical particles with a mass mobility exponent of close to 3. The flaming ones with mass exponent around 2.2 are purely fractals, and the transition is between 0.92 and 0.96. And this, we propose a relationship between mass mobility exponent and MCE that can serve as a test to when to apply me theory when considering biomass burning aerosols. We could also did the evolution of the particle size distribution for the flaming and for the smoldering fires. As you can see, the white line indicates the evolution of the geometric mean diameter of the distribution. Flaming dominated burn mostly produce ultrafine particles, whereas smoldering dominated particles are dominated by fine particle mode. And the electron microscopy image of filter samples collected using smoldering fires, and flaming fires are quite distinct. These are the images that you can see. Next, this is the chamber. Actually, this was the picture taken while it was under construction. It doesn't look like this now because it's covered with a cardboard and aluminum foil. But this is what it physically looks like. It's 9 cubic centimeters in size. And this allows controlled studies. We can study the evolution of specific compounds and particles produced from specific fuel. In this process, the smoke and gas produced from the tube furnace are directed into the chamber using a heated stainless steel tube, but heated to 200 degrees Celsius. The volume is well mixed within 10 to 20 minutes after the injection because we have a mixing fan inside. And if we burn about 0.5 grams of fuel, we can produce up to 600 to 800 micrograms of meter cubed of mass loading in the chamber during smoldering dominated fires. So this work is done by Damon Smith, former student of mine, and the details of the chamber are published in Aerosol Science, AQR. I forgot what that stands for. Okay, and then look at the measurement of extinction, which is we're measuring optical properties. So we measure extinction, scattering, and absorption of those. So the extinction measurement is done using cavity ring down system. In our lab, we have an OPO and a neodymium YAG that produces light at 532 and 355 nanometers. That the 355 is used to pump the OPO, so we can get all sorts of colors because it's tunable laser. So, but the cavities mirrors have to be different for different wavelengths. So we have constructed two cavities. So we can do extinction measurements from 420 to 500 and from 510 to 590 from the same light source. And so we have a shorter cavity for UV absorption for brown carbon. We have the longer cavity for visible absorption for black carbon. And these measurements match with what we measure with AE33, which is L-thalometer and the nephelometer. The cavity ring down spectroscopy is actually a very sensitive absorption technique. The effective absorption path lengths could be as long as 10 kilometers. The sensitivity is independent of intensity fluctuations of the laser. That's one advantage. And so it's a very simple system where two highly reflecting mirrors, reflectivity up to 99.999, if even more, and the decay time is determined by measuring the time dependence of the light leaking out of the cavity. So at each round turn, the intensity of the light coming out decreases, forming some kind of a decay profile. And so the key assumptions are the loss in mirrors is considered to be 1 minus the reflectivity, the transmission T, and we can write the equation of the change intensity as a function of distance. This can be changing variables from position to time. We can write the equation as a time equation where we look at a differential change of the intensity, which leads to the intensity as a function of time, which is expressed as exponential of time over tau zero, where tau zero is a photon lifetime within the cavity. So this is really what we call the ring down time of the empty cavity. When we have a sample, there is an absorber, then we have to apply Beer's law, where the intensity change is proportional to the cross-section, to the extinction coefficient, and the distance dz. RL is the distance, the ratio of d over LA, where LA is really where the sample is, and d is the distance between the mirrors. The space between the mirrors and the sample containing part is actually flown with nitrogen to keep the mirrors clean. And we already have the time. So the differential loss, cavity loss, including the absorber, would be expressed in this form, and the cavity time constant 1 over tau will be related to the cavity time constant, the photon lifetime plus whatever absorption takes place when the beam goes through the absorber. And so we have absorption or extinction coefficient is expressed as a difference between the reciprocal of the time constant, the cavity time constant minus the photon lifetime. Now, so this is what we really see. There is without sample and with sample, the decay profiles are different, and the extinction is determined from that. And by knowing the number density, we can also calculate the cross sections. So this extinction could be a result of extinction due to gas particles and particles. So we ignore the extinction due to the gases. So this provides us with extinction of the light by the aerosol particles, which is really the sum of scattering and absorption. We measure absorption independently using the ethylometer. Of course, again, we use Beer's law to do that. The absorption extinction coefficient. The ethylometer measures absorption at 7 different wavelengths. Typical equations used for this are the attenuation coefficient for optically absorbing aerosols can be determined by evaluating the light attenuation rate of change passing through a particle-laden filter. The equation that's usually used for this purpose is the second equation, which is this one, if you see my light. So S in this equation represents the spot area. F in is the aerosol flow rate, and delta T is the sampling time, which is about 1 minute resolution. And the attenuation is measured at 370, 470, 520, 590 nanometers. And this is actually calibrated against a multi-wavelength absorption analyzer with our collaborators in Genoa, Italy. Now, we also claim that we can introduce the aerosols into an environment that they are produced. So since we're looking at African emissions, and in the tropics, there is high humidity, high temperature. So aerosols, if there is a wildfire in that region, the aerosols that are produced are introduced into high humidity environment. So we try to reproduce that by introducing the aerosols from the tube furnace into a chamber that's already humidified. So in order to create the humidification, we use zero air passing through quark glass bubbler. This is filled with ultra pure water and in a heating mantle. And we can introduce the vapor into the chamber and measure the relative humidity using a hygrometer that's attached to the chamber. So we can achieve 60 to 75% humidification. Actually, this was started by Megan again in her previous paper, where we did hygroscopicity measurement of eucalyptus and cow dung aerosols. And this was again in collaboration with Professor Awaku, of course, University of Maryland. So since this talk is being broadcasted from University of Maryland, that was the work that we did with her collaboration. And then we generate nitrate radical to study the aging, nighttime aging. This is a process that is followed. We have nitrogen dioxide injection about 1.2 liters per minute, about 500 ppb, and ozone generator produces about 220 ppb of ozone, and in the process we produce about 250 pptb of nitrate radical. The aging conditions, we have dry and humid. So the dry is about 10% humidity, high humidified chamber is about 70. We do dark aging, which is about 3 hours in the chamber. Photo aging is about 1 to 1.5 hours with the UV lights on. And oxidation experiments are done by using nitrate radical introduced into the chamber under high humidity. That's 70%. And so this is what the setup the laboratory looks like, and the chamber at the back, and all the laser tables and the optics and the other accompanying instruments, SNPS and so on. So these are typical experimental time series. These are examples usually taken from the Ethiopian cow dung, which examine the effect of relative humidity, aging, oxidation conditions, humidified controlled experiments, and so on. So the first one are those undergoing nitrate radical oxidation, and B corresponds to are showed in terms of NOx, ozone, carbon dioxide, relative humidity, temperature, and particle mass concentration. The dotted lines, the vertical dotted lines, the dotted line across the graph is the calculated partial vapor pressure. Burn and light start times are distinguished by dashed black lines. These are the vertical lines. So the time of burn and the time that light is on and so on. And the sampling times are indicated with yellow rectangles in both figures. So the rectangles indicate the aging times, so the dark aging or photo aging. So these are the different conditions in the experiment. And we also, actually the measured quantities in this work are mass extinction coefficient, mass scattering coefficient, single scattering albedo, and we also measured, I believe, the first time the extinction emission factor. I looked through the literature. The only thing I saw is absorption emission factor. That's reported in literature. This is extinction emission factor, and I'll talk about it when we talk about the results. So these are some of the results. Again, you can look this through the paper, and I tried to reproduce them on the slides. So the first one is the effect of relative humidity on mass extinction coefficient and mass scattering coefficient. As you can see, the orange diamond represents dry conditions, 0 to 10% humidity, and the blue triangles represent humid measurements from 60 to 75. And so the results clearly show that relative humidity causes lower mass extinction coefficient and mass scattering coefficient values. Changes are higher for mass extinction coefficient. The average decrease in each case is about 2.3 meters squared per gram. This is the same quantity for mass absorption coefficient. So that's the same story. And then when you look at the photoaging experiments, brown circles indicate average fresh measurements, and green squares indicate average photochemically aged measurements. And aging again causes higher mass extinction coefficient, and mass scattering coefficient changes are larger for mass extinction coefficient. There is one outlier. One of the fuels showed slightly different values, much higher than most of them. This is Mosothela. This is a plant that's collected in Botswana. Actually, further chemical analysis studies of some of the Botswana fuels also revealed some different biomass burning markers which can be used to identify wildfires in the region. This is extinction efficiency. The extinction efficiency of aerosol actually describes how strongly tiny particles in air block and bend light through scattering and absorption. So efficiency is higher at shorter wavelengths, ultraviolet and UV, and changes as fresh emissions age. For example, fresh wildfire smoke has a mass extinction efficiency of about 2.5 to 3.2 meters squared per gram, and then it rises to 6 to 7 meters squared per gram after 1 day of atmospheric processing. So for a given mass extinction coefficient defined as a dry extinction coefficient per unit mass concentration M on aerosol population. So that the equation that we used for this plots is the last one, the equation at the bottom. But one can also describe the aerosol population by size bins, those especially if they are measured by sizing instruments, and use the Mie theory, assuming spherical and internally mixed particles. One can estimate the extinction cross-section using the equation given, where n is the total number of concentrations and di is, of course, the diameter of the size bin I, and alpha I is the extinction efficiency of diameter di at a refractive index ni. And f is actually the fraction of aerosol number at the size bin I. The mass is also calculated the same way, so that one can also calculate the mass extinction efficiency. Now, this is for photo-aged experiments. Again, dark aging and photo-aged mass extinction coefficient and mass scattering coefficient with nitrate radical experiments. The fuels are listed along the x-axis. So this is done for fewer fuels, not the whole suite of fuels. There is an average change in mass extinction coefficient of about 2.5 meters squared per gram. And the same with the dark aged for absorption. Now, this is extinction emission factor. This represents the extinction cross-section in meters squared emitted to the atmosphere per kilogram of fuel consumed. So determined according to the equation given. It's vital for actually quantifying the aerosol climate impacts, tracking atmospheric pollution, and modeling radiative models. So this is, in most literature, absorption emission factor is measured, but this is probably the first time the extinction emission factor is measured in this work at 500 nanometers. Now, the scattering angstrom exponent and the absorption angstrom exponent graph plots provide actually valuable insight for identifying the nature and source of aerosols under observation. So in this figure, you can see that this angstrom matrix divided to indicate different sources of aerosol labels were derived from. So as you can see, the red, so this gives you the absorption angstrom exponent dependence on MC. And so let me go back. Let me say this again. There are the absorption angstrom exponent values, as you can see, range from 1.5 to about 3.3 under fresh conditions, and between 0.7 to 3.2 under dark conditions. So these are the AAE are given by red circles, indicate fresh measurements, green squares indicate dark measurements, and blue triangles indicate the aged measurements. So you can follow the colors. The scattering angstrom exponent values, on the other hand, show a range of 1.3 to 2.2 in fresh conditions, 1.2 to 1.9 in dark aged conditions. For photochemically aged conditions, absorption angstrom coefficient values range from 1.5 to 2, and the scattering angstrom exponent values range from 1 to 1.8. So the range of values for this decreases further upon photoaging as well as with oxidation. So that's that tells you what the source of this map actually is an indication of the source of the aerosols under observation. So the summary, the relative humidity causes lower mass extinction coefficient and mass scattering coefficient. Changes are higher for mass extinction coefficient. Photochemical aging causes higher MEC and MSC, and higher mass extinction coefficient and mass scattering coefficient values observed upon dark aging with nitrate radicals. Not the same for all fuels, though. All optical properties also showed fuel dependency, and the typical values that were observed are also shown in the next column. Now, the impact on radiative forcing is really of interest because when we measure optical properties, we are interested in what would be the impact of these optical properties on radiative forcing. So to conceptualize these cross-sections within the climate framework, we actually used the change in radiative forcing by Wong in 1995, where tau scattering and tau absorption are the scattering and absorption optical depths, respectively. Rs, in this case, is the surface albedo. Beta is a fraction of the upward scattering radiation. The scattering and absorption optical depths are the product of path length and mass loading and mass cross-sections. So for our studies, the path length and the mass loading were the same. So this simplifies the equation to use the mass scattering coefficient and mass absorption coefficient instead of those other values. To calculate gamma in this equation, we used estimated values of 0.15 for Rs. Rs, remember, is a surface albedo, and 0.3 for beta, resulting in gamma of 0.72. Since we are interested in the average relative change in direct radiative forcing for various values of mass scattering coefficient, calculations in this work is based on basically the extinction minus absorption measurements. So the scattering is not directly measured. It's measured as a difference between the extinction and the scattering. So the path lengths, as I said, the path lengths and the mass loading are equal. Rs is the surface albedo estimates and beta, as I indicated. So what are the climate implications? So these are some of the changes we see: fresh, photo-aged, photochemical aged, and so on, under dry and humid conditions. Average decrease or increase factor: cooling decreased by 0.88, cooling decreased by 0.9, and so on. We also try to use the tropospheric ultraviolet visible radiation model from NCAR to see so the model ran with solar zenith angle of 0, a column of ozone about 300, and under cloudless conditions. The optical depth was taken as 0.4 for each base case, which resulted in a total downwelling of about 1.71 to 1.719 watts per meter squared per nanometer, depending on single scattering albedo, from 549 to 551 nanometers. For mass extinction coefficient, the optical depth was scaled to each comparison. Humid condition resulted in an average warming of about 0.25 and 0.10 watts per meter squared per nanometer for both fresh and primary photo-aged aerosol without added nitrate radicals, respectively. And finally, this wasn't part of this paper, but I just want to mention the work done to parameterize and correct the ethylometer for African fuels, because the ethylometer had its own issues. There are known problems with ethylometer, so one has to calibrate it with more accurate instruments like photoacoustic system, which we didn't have. And we also used the correction that's developed by the Italian group in the previous work. But this is just to show you how Megan was also part of this project and traveled to Los Alamos to do the parameterization and correction of the ethylometer for African fuels. And this was led by Mark Fiedler. And this is just the ethylometer for African fuels. This was done after the paper on SNT was published. So I guess this is what I have, about 45 minutes, so I'm ready to take some questions.
Well, great talk. Thank you so much for that. We will open up for questions now, so feel free to raise your hand to unmute or drop anything in the chat if you would prefer to do it that way. But we'll have about 15 minutes for questions here. Okay, looks like we have a question in the chat. They say, thanks for the talk. Did you control the temperature of the combustion in the tube furnace for different fuels?
Yeah, so we calibrated the temperature with MCE. So the furnace can be run from anywhere from 300 to 800 degrees Celsius. So what we consider flaming and what we consider smoldering is calibrated with, so the temperature of the oven is calibrated with the MCE that's produced. So typically 500 degrees Celsius corresponds to smoldering fires with the MCE of about 0.9 and below.
Maybe I could ask a question going off of that a little bit. With climate change and temperatures changing and things like that, how do you foresee that changing kind of your results here? Could you almost extend that out with how the conditions might be changing within the African continent with different climate change effects?
Well, there's a lot of unknown in that continent. And as I indicated, most of the fires are in the tropics. And the tropics are heavily high humidity and high temperature region. And not only that, it's also the largest source of biogenic emissions. So the chemistry is going to be very complicated. It's not just anthropogenic emissions, but there is huge amount of biogenic volatile organic compounds that will interact with aerosols to produce chemistry that we still don't understand. So to some extent, that's what we're trying to initiate here by changing the humidity in the chamber and introducing the particles into a humidified chamber. And we're trying to also change the temperature. Normally the chamber is maintained at room temperature, but currently we're also trying to change the temperature of the chamber itself. So by introducing hot air into the chamber, so that because high humidity comes also with high temperature.
Right.
In order to reproduce the region's chemistry properly, you have to increase the temperature of. So one of the work that we're doing is trying to understand the SOA, the secondary organic aerosol yield in the chamber as a result of biogenic volatile organic compounds in humidified chamber at higher temperatures.
Oh, thank you. Yeah, definitely very complicated. So we have some more questions in the chat here from Chad Bailey. I noticed an increase in particle mass in one of the smog chamber time series. Any speculation as to how much new particle formation is responsible for the changes in optical properties?
I don't anticipate new particle formation. There could be some coagulation that would change the particle size, but I don't think any secondary organic aerosols are formed in this setup.
Next question is, did you have a chance to compare your generated combustion aerosol with naturally produced fire aerosol?
No, but we did filter sampling in the region. So one of the earlier work by one of my postdocs, Biomass, is to compare the chemical composition of filter samples collected in Botswana with laboratory generated filter samples by using the setup that I showed you and looking at the chemical composition of the two. That's the closest we came to real life events.
Right. And follow up to the first question, you mentioned 500 degrees Celsius corresponding to smoldering. Does that mean that's the threshold for smoldering to happen, less than 500 degrees and flaming greater than 500 degrees?
So I wouldn't put the temperature as a measure because different ovens operate differently. So it's really the MCE that matters. The modified combustion efficiency is what determines whether we have smoldering fire or flaming fire. And those could be initiated at different temperatures depending on the type of furnace you're using. So this is strictly for our furnace, but not all furnaces are made the same way.
And one more question. Can you elaborate more on the enhanced absorption after dark and photo aging? Any insight on the chemistry?
There is, I would refer you, and chemistry is not, I'm not very conversant of the chemical process that take place, but there is a paper in our group by Biomass that analyzes the chemistry of this. Basically, Megan and Bios worked together. So he did the chemical analysis. And so there's a detailed work on uh, environmental science and technology article in 2024. Actually, that article was selected as the fourth best paper for that year, 2024. So that I would refer you to that paper to look at the chemical aspect of it.